All right, welcome to today's lesson. We're going to be continuing to just kind of get a better handle on using Taylor series. We're going to be working with Taylor series today in 10.8. And at the root of everything that we're going to be doing over the next couple days, we really just need to remember the formula for our Taylor series and Taylor polynomials, which is, in particular, the main big important thing is right here. I guess you can also remember this, but at least as long as we're remembering the formula for the terms in the series, that it's the kth derivative at a over k factorial times x minus a to the k, where a is the value we're generating the Taylor series about. Okay, we're going to need to remember that today and in the days to come. All right, let's just jump straight into some examples and get into practice. Okay. So we want to write the first order Taylor polynomial for this function we see up here, the cube root of x, about x equals 16, right? That's what we're looking for. And use it to approximate to the cube root of 15. And then, is this approximation an over or under approximation? Explain our reasoning. Some of this seems a little new, but at least these last two steps, we've seen stuff similar to that this year already. All right, so starting to write that polynomial, this polynomial, we need to make sure we remember that formula for our Taylor series. We're going to return to this a lot. Remember, we're looking for f, the kth root of f at a over k factorial times x minus a to the k for each of our terms in our Taylor series, all right? And we know here that we're trying to do the first order Taylor polynomial at x equals 16. So that means our a value is going to be 16, and our f of x, in this case, is going to be the fourth root of x, which is x to the 1/4, right? And here's how I like to set up, if we're just doing the first order Taylor polynomial, here's how I like to set it up. I like to say, okay, I need the first, because our sum is going to start at k equals 0, so I need the 0th derivative. So that's f, just normal f of a. In this case, that's f of 16, which is the cube root of 16, right? Cube root of 16, which is 2. All right, so there we go. So we take our a value, we substitute it into our function, and then for our next term, we need the, now k was 0. Now we're going to take the first derivative at a, divide it by our things, and multiply it by our things. So let's start with the derivative part first. So now I need the first derivative. This, I realized over here, my exponent turned out to not really look very much like an exponent. So I'm going to get rid of that. I'm going to come back over here and make this a little more clearly a 1/4 exponent. All right, because then we're going to need to take the derivative of this thing right here. All right, so we can do that. Our first derivative of x, I'll bring down the 1/4. This will be x to the, I need to subtract 1 from the exponent, so it's negative 3/4. I made a mistake on this the first time I did this video, so this is also a correction. Hopefully I will edit it pretty seamlessly into this video. All right. So there's our derivative, which I guess if we want to, we can think about as 1/4 times the fourth root of x cubed, if that helps. All right, so then we need that. We need the first derivative at 16. So we're going to plug 16 into this thing we got over here. So that's 1/4 times the fourth root of 16 cubed, which is going to give us 1/4 root of 16 is 2. 2 cubed is 8. 4 times 8 is 32. This is 1/32. All right, I only need the first order Taylor polynomial. And as long as I have the 0th derivative, so my original function, my first derivative, now at the first order level of things, so I can actually write out what this polynomial would look like. It follows this pattern up here. So my p sub 1 of x is going to look something like this. It's going to be the 0th derivative at a, so that's 2, over, I'm in my 0th term, so it's 0 factorial, times x minus a, which in this case is 16, to the 0th power, plus Then I move on to my next derivative, my first derivative. This will be 1 over 32 over, I'm in my first term now, my first derivative, so 1 factorial, x minus 16 to the first power. All right, simplifying this, I get p sub 1 of x is going to be equal to, we got to remember that 0 factorial is 1. We got to remember that. 0 factorial is 1. So this is really 2 divided by 1 times something to 0. So that's 1 also. This really gives us 2 plus 1 factorial is 1. So that's 1/32. 1/32 x minus 16 to the first power. All right, there we go. So this is my first order Taylor polynomial. Notice I needed f of 16 and f prime of 16 to be able to get that by plugging into my little formula up here. So this is my first order Taylor polynomial, and we want to use it to approximate. We want to use it to approximate to the 4th root of 15. Okay, so this is going to get interesting. We now know p sub 1 of x. So let me try plugging in 15 now, because this Taylor approximation down here will approximate this function, right? And if this polynomial is approximating this function up here, then if I want the 4th root of 15, I should be able to just plug 15 into this and get a kind of approximation. So plugging in 15, I get 2 plus 1 over 32 x minus 16, right? I need to plug in though, plug in an x value of 15. That'll be right there. All right, so this means my approximation is 2 plus, 15 minus 16 is -1, 2 plus 1/32 times -1. So I'm just going to go ahead and call this then minus 1/32. Remember, you don't have to simplify these things for me, but can in this place it's not too bad. So this is 64/32, so we can call this 63/30. Okay. It makes sense that this number is less than 2 because we're approximating the 4th root of 15. The 4th root of 16 is 2. This is going to be smaller, so this makes sense here. So we just use it to approximate the 4th root of 15 now. Is this approximation an over or under approximation? Explain your reasoning. We've seen stuff like this before when we were looking at tangent line approximations, and actually this first order Taylor polynomial really is just a tangent line approximation. Here's our derivative at our point. Actually, we should use this one. Here's our derivative at our point. Here's x minus the x value, right? We added over the y value at 16, which was the 4 through 16, so it's 2. So really this is just a tangent line approximation. So we can kind of base our reasoning off of that if we want to. Which means for our tangent line approximations, since we were using the first derivative, we need to look at the second derivative to figure out concavity. All right, let's find our second derivative. Our second derivative, f double prime of x. I can come over here and continue this process. Is going to be the derivative. That's going to be -3 over 16, right? -3 over 16. X to the, I'm going to subtract another one from here. X to the -7/4. All right, but here's the key takeaway, right? The second derivative, no matter what x value you plug in here, is going to end up being negative. And thinking about it earlier in calculus, this makes sense. This would mean that our graph is concave down in this case, right? And our cube root function is concave down. It's always concave down. So if we were just thinking about it from like tangent line stuff, the second derivative is negative, our graph is concave down, so our approximation is going to be an over approximation. But we can extrapolate that to our Taylor polynomials also, because they're not just tangent lines. Our Taylor polynomials are essentially trying to get a hold of and follow this curve. Because we know that the derivative of this thing that follows the derivative that I stopped at is negative, it means that the derivative value I'm using is decreasing, right? So concave down here, which means my Taylor polynomial is going to over approximate it. Essentially, since the derivative that follows it is negative, that means the derivative I stopped at is decreasing, which means that my Taylor approximation is going to over-approximate this curve because the derivative that follows it is negative, all right? If the derivative that follows it would be positive, like the derivatives were increasing, whatever, we have a super concave up kind of curve, then our Taylor approximation, because we would stop at some derivative, that would be part of an increasing function. Our Taylor polynomial is just going to under-approximate everything. So we can still use the same kind of reasoning we did earlier in the year. All right. So we now know that the second derivative, the derivative that follows where I stopped, is negative, which means then that this derivative value is decreasing, which means that our Taylor approximation is going to overshoot the actual thing because the value is actually going to be less than this as I continue out. All right. So what does that mean for us? We can say that P sub 1 of 15 is actually going to be greater than, it's an over approximation of the actual value of the fourth root of 15. We can say because, language will seem a little different this time, but we can say because the first derivative, which is where I stopped, right? That was the last derivative I used over here, because the first derivative of x is decreasing. And since it's decreasing, that means that if I added the more information about the derivatives that follow it, like the second derivative, my graph is going to keep curving downward, which means that my approximation is going to be above it. But remember, f prime is decreasing simply means the second derivative is negative. If I stop the second derivative, I can look at the third derivative and so on and so forth. Okay, so there we know approximation is an over approximation, and it's because that first derivative is decreasing because we found the second derivative is negative. That meant it was concave down, so our Taylor polynomial over approximated it. All right, there were some big key takeaways in this problem that I want us to kind of center in on and just kind of hold in the back of your mind. Okay, so let's go ahead and let's take a look at those. A Taylor polynomial, a couple observations here that are really important. A Taylor polynomial is actually, generally speaking, a good approximation for function for all x values. I know we center a polynomial around some x value, but it really is a good approximation of a function for all x values, not just the ones kind of near it. Obviously, the more terms you add to your polynomial, the better it gets, but you can actually use your Taylor polynomial to approximate any value, really. In this case, a Taylor polynomial over approximates a value of a function if the derivative for the ending term, so think about that last term we did was at the first derivative. A Taylor polynomial over approximates a value like the one we just did if the derivative for the ending term, if the derivative for the ending term is decreasing. So in that case, the one we just looked at, the derivative, that first derivative we stopped at, when we took its derivative, we found out its derivative was negative, so that means the derivative we stopped at was decreasing, so our polynomial over approximated it. A Taylor polynomial will under approximate a value if the derivative of that ending term is increasing. So if we had taken that derivative and found out that that last derivative, when we took its derivative, so in this case the second derivative, was positive, that would mean the last derivative was increasing, which would mean that our Taylor polynomial would sit underneath the graph. It would be less than it. And so we would under approximate the graph. All right. So if we keep going, let's look at another example. Let's let j be a function having derivatives of all orders where x is greater than 0. Selected values of j in the first four derivatives are indicated down here. The function j and these four derivatives are increasing. Ooh, that's probably going to be important. We just talked about how functions and derivatives are increasing. We want to write a second degree Taylor polynomial for j about x equals 1. Use it to approximate j of 1.1. And is this approximation greater than the actual j of 1.1? And explain your reasoning. All right. So let me try to leave that there. Let's give it a shot. Second degree Taylor polynomial. Remember my formula I need to keep in mind is our Taylor polynomial formula that we are looking at all week. F, the kth derivative of f at a over k factorial times x minus a to the k. In this case, our a value, we're going to approximate around a is 1, and our function is j of x, which we're not given the actual function, but we're given a bunch of derivatives, so that'll be useful. So let's write out then we want the second degree Taylor polynomial, second degree. So let's do this. We need to find f of 0, the 0th derivative at a. So we need j of 1, right there, 10. So it'll be 10 over 0 factorial x minus 1 to the 0 plus, then we'd move over, we want the first derivative at 1. That's f of k. K is now 1, so the first derivative there, which will be 11 over, we need k factorial going out, our first term, and then x minus 1 to the first power, plus, then we got to move over, we need the second derivative at that a value now. So the second derivative at a value is 14 over 2 factorial x minus, I almost wrote 2, x minus 1 squared, because k is now 2. We can clean this up a little bit. This means our polynomial, second degree polynomial, would be, remember 0 factorial is 1s, that'll be 1, so it's 10 plus 11 x minus 1 plus 2 factorial is 2, so 14 divided by 2 is 7 x minus 1 squared. Okay, so we found our second degree Taylor polynomial. We want to use it to approximate now j of 1.1. We don't have to worry too much about simplifying. Remember, that won't matter too much for us. We want to approximate j of 1.1, so I plug into my polynomial. That's 10 plus 11. 1.1 minus 1 is 0.1, plus 7 times 1.1 minus 1 is 0.1 squared. All right, so here is my approximation of j of 1.1. Now, is this approximation going to be greater than the actual j? Well, what do we know about j? We know that j and all its derivatives are always increasing. So this function is just kind of increase. Everything's increasing, 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 increasing. All right? Everything's increasing, increasing, increasing. So my approximation here, even though I ended here, it's going to be okay approximation, but this final derivative keeps on increasing. So this value is going to be less than the value of the actual function, because if this actual function is just keeps on increasing, and I'm kind of laying my Taylor polynomial to try to copy it, this final term, because the actual derivative just keeps on increasing, is going to have to be less than that. All right, so I'm going to say my approximation p sub 2 of 1.1 is less than j of 1.1, because let's see, we ended here at this derivative. We can say because j double prime, because we ended the second derivative of x, is increasing on our interval, which I think is 1 to 4. All right. Cool. We've seen a couple examples now. Go ahead and get rid of that. And moving on. Here's what I like you to do. I'd like you to practice a whole set right now. I want you to practice. There's 1, 2, 3, 4 different kinds of practice problems to think about applying your understanding of Taylor polynomials and Taylor series right now, okay? I want you to go ahead and try them for a couple minutes. When you're finished, pause the video and come back and check. All right, let's go ahead and get started. Use the table above, so we're using that same table to write the third degree Taylor polynomial for j, about x equals 2, and use it to approximate j of 1.9. Is this approximation greater than j of 1.9, and explain your reasoning? Okay. Seems very similar. This is meant to be kind of a repeat, make sure you understand kind of thing. So we need the third degree Taylor polynomial. Again, we'll remember that formula f. We need the kth derivative of f at a over k factorial x minus a to the k. We want the third degree Taylor polynomial, so we want p sub 3 of x, and we want to center it at a equals 2. And j of x is still our function in question. Okay, so we need to go up to our table. I want to work it kind of up here just so we can be looking at my work, and then I'll scroll back down to the actual problem. All right, we're interested in at a equals 2, right? So a equals 2, my function value is 13. So it's going to be 13 over 0 factorial x minus 2 to the 0 plus, then I move over to my first derivative. That'll be 14 over 1 factorial x minus 2 to the first power, plus, then I move over to my next one. My derivative, my second derivative at 2 then is 150 over 7 over 2 factorial x minus 2 squared, plus my last term, 160 over 3. Wait, we need, I skipped one. So that's the j, first derivative, second derivative, third derivative, right there. Third derivative then is 160 over 3 over 3 factorial. This is x minus 3, or x minus 2. X minus 2 cubed. There we go. So there's my my third order Taylor polynomial. I just got to clean that up a little bit. So let's go down now that we have that. We can clean this. All right. So what is our third order polynomial going to be cleaned up? Third order is 0 factorial is 1. So this is 13 times 1 plus 14 divided by 1 times x minus 2. Remember, this is just our tangent line approximation, but we keep going to make it a little better. That's what a Taylor polynomial does. So this is 150 divided by 7 divided by 2 factorial is 2. So that'll be 150 divided by 14, but I can simplify that a little bit. So that'll give me 75 divided by 7, x minus 2 squared, plus, let's see, 3 factorial, that's 6. So this will be 6 goes up here. That'll be 160 divided by 18. 160 divided by 18. So if I do that, that'll give me 80 over 9 x minus 2 cubed. Because 3 factorial is 3 times 2 times 1, so that's 6. Divided by, multiply into the denominator. 6 times 3 is 18, and 2 goes into 160. 2 goes into 18. There we go. So here's my third order Taylor polynomial. We want to use it to approximate now 1.2. So p sub 3 of 1.2 is 13 plus 14, 1.2, 1.9. 1.9 minus 2 is going to be negative 0.1 plus 75 sevenths. 1.9 minus 2, we'll shortcut that. 1.9 minus 2 gives us a negative 0.1 squared plus 80 over 9, same thing, negative 0.1 cubed, whatever that gives us there. Is this approximation greater than j of 1.9? Here's our approximation. Well, what do we know about all the derivatives? We know, again, all the derivatives of j are increasing, increasing, increasing. And so this approximation, if the actual j function is increasing, 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 if we stop here, we're going to keep undershooting it because this derivative is actually increasing, so we're not getting all the things that we should. It's going to be less than the actual value. Imagine it was touching there, less than the actual value there. So I can say p sub 3 of 1 point, I wrote 1.2 over here, didn't I? That's silly of me. No wonder I made that mistake earlier. I said 1.2, meant to say 1.9. 1.9, there we go. P sub 3 of 1.9 is going to be then less than the actual function j of 1.9 because, let's see, in this case we stopped at the third derivative because j triple prime of x is actually increasing on 1 to 4, and because this derivative, the actual derivative function's increasing, we're not getting all of the values after it, and so our approximation is going to be less than the actual function. All right, take a look at the next one. Use the table above to write the third degree Taylor polynomial for j about x equals 3. Is this Taylor polynomial only a good approximation for the values of j near x equals 3? Okay, I'm going to move up to the table. Third degree Taylor polynomial at x equals 3. Let's take a look. Okay, third degree Taylor polynomial at x equals 3. We go back to that same formula. You just got to keep that in our heads, right? F of kth derivative of f at a over k factorial x minus a to the k. So again, third degree polynomial this time. That is a strange looking p. If your doctor says that, that's no good. But in math, it just means we got to correct, look a little better. All right, the third degree, third order Taylor polynomial here then would be x p sub 3 of x is, we're looking at x equals 3. That's our a value. All right, so we start with, here we go, the 0th derivative at 3, which is 9 over 0 factorial x minus 3 to the 0 plus, we move on to the next one, 90 over 8. 90 over 8 divided by 1 factorial x minus 3 to the first power plus, move over to the next derivative, 90 over 7 over 2 factorial x minus 3 squared plus, move over to our next one, well, the third order, so we're going to the third derivative, 97 over 7, 3 factorial x minus 3 cubed. All right, clean this up. P sub 3 of x, remember 0 factorial is 1 times 1, so that's 9 plus 90 divided by 8 divided by 1 factorial, that's 1. So 90 divided by 8, we can actually simplify that a little bit. 2 goes into both those, so that'll be 45 over 4. X minus 3 to the first power plus 2 factorial is 2, so we're going to multiply that up there. So that's 90 divided by 14. 2 goes into both of those. So that'll be 45 over 7. X minus 3 squared. Then plus 97 over 7 divided by 3 factorial. 3 factorial, remember 3 factorial is 6. So this is going to be 97 over 6 times 7, which is 42. X minus 3 cubed. There we go. So there is our third order Taylor polynomial, third degree Taylor polynomial for j centered at a equals 3. Come back down over here. Make sure we did all that right. We did the third degree Taylor polynomial for j at x equals 3. And is this a good approximation for the values of j? Only a good approximation of the values of j near 3. Remember, one of the great things about Taylor polynomials is they will be pretty good approximations for things not just near 3. So the answer here is no, in fact. For the general function j, no, it works kind of all along, okay? We, generally speaking, use these for all x. If you want to go back and look at that video that I posted the first day that you took notes on, and they explain how we can use the approximation to approximate pretty well a function all along its domain. All right. Okay. We had 2 more practice ones. One, we just want to write the third order Taylor polynomial. Great. We know how to do this. Again, same old formula. The kth derivative of a over, not a factorial, over k factorial times x minus a to the k. All right. That is our formula. We want the third order Taylor polynomial at x equals so this is going to get interesting because we want, think about it this way, we want a equals 1. We also know that f of x, our function we are approximating, is the natural log of 2 minus x. So we need all of our derivatives. So we want f of 1, which is the natural log of 2 minus 1, which is natural log of 1, which is 0. But now we need this derivative. So I'm going to write its derivative over here. The first derivative is, see, the natural log of 2 minus x. So that's going to be 1 over 2 minus x times the derivative of the inside, which is negative 1. So it's going to be negative 1 over 2 minus x. So now there's my first derivative. I need the first derivative at 1, which is going to give me negative 1 over 2 minus 1. So that's going to be negative 1. All right. If it helps for the following derivatives, I'm going to actually write this out in power kind of way. This is going to be negative. I'm going to raise this up there. 2 minus x to the negative 1 is really what we're looking at there. So to get my next term, I'm going to need the second derivative. The second derivative, take the derivative there, bring down negative 1 times negative 1 is going to be positive 2 minus x to the negative 2 power. All right, so I need the second derivative at 1, which is going to be 2 minus 1. That's 1 to the negative 2. So that'll give me 1. Then I need my third derivative to get my next term. My third derivative, I'm going to take the derivative here, so I'm going to bring down negative 2. That'll be, wait a minute, I forgot to do something, didn't I? I forgot to multiply my second derivative here. I brought down my negative 1 for my power rule, yes. I kept the inside subtract 1, but I forgot to multiply by the derivative of the inside. So this is going to actually be negative in here, isn't it? So my second derivative is negative. We always got to look out for our power rules and the little rules to make sure we don't make a mistake. Caught it. Okay, so let's actually recheck this third derivative then. Taking the derivative, we bring down the negative 2. Bring that down. It will give us positive 2 times the quantity to, make sure I continue as best as possible, 2 minus x. So power rule, bring down the outside, keep the inside, multiply by the derivative of the inside, which is negative 1. There we go. So our third derivative at 1 is going to be, interesting, 2 minus 1 is 1 to negative 3. That's still 1 times negative 2 is going to be negative 2. So now I have all of my derivative values at 1. And I now know what each of the values of those things are. Let me double check. I get freaked out now that I've done a derivative wrong. That'll be positive. All right, we look good. Okay, so I want the third order Taylor polynomial, so p sub 3 of x is going to be my first number I got. This is basically just like my table. So 0 divided by 0 factorial x minus 1 to the 0. And I kind of keep going. Plus my next number over here was negative 1. So negative 1 over 1 factorial, my factorial, x minus 1 to the first power plus negative 1 over 2 factorial x minus 1 squared plus negative 2 over 3 factorial x minus 1 cubed. So I've now laid out all of my derivative values divided by their factorials, so we can clean this up. P sub 3 of x is 0 divided by 0 factorial. That's going to be 0 plus, let's see, that's going to be negative 1 divided by 1, so that's going to be negative x minus 1 to the first power. That's going to be negative x minus 1 to the first power. This is also going to come out to be negative, so minus 1 over 2 factorial is 2. X minus 1 squared. Negative 2 divided by 3 factorial. 3 factorial is 6. So this is going to be minus 1/3. X minus 1 cubed. So there we go. And these are also what people say the first 3 non-zero terms, because their first term came out to be 0. All right. Here's my third order, third degree Taylor polynomial. Okay. Keeping on. Let's see. Practice this one. Selected values of the function f and its first 4 derivatives are shown on the table. What's the approximation of the value of f of 2 obtained using the third degree Taylor polynomial? Wow. Deja vu. Remember, we want the kth derivative of f at a over k factorial x minus a to the k, to the 2. That don't make no sense. Okay, we want the third degree Taylor polynomial. Looks like we got all the things we need here. We just got to lay it out. So our third degree Taylor polynomial is going to be centered at f of 1 is, let's see, the 0th derivative is 2 over 0 factorial x minus 1 to the 0 plus, oh man, this got funky. I'm gonna add something in here. I'm gonna add it to my this should say, I'm gonna change it on my PDF. This should say the first, the second, and the third. I'll change it on yours so you don't have to deal with that problem. But imagine this is first, second, third derivative now. Okay, so I did my 0th derivative plus my first derivative here is negative 3 over 1 factorial times x minus 1 to the first power plus my second derivative at 1 is 6 over 2 factorial x minus 1 squared plus my third derivative is negative 8 over 3 factorial x minus 1 cubed. There we go. We got to clean that up. 0 factorial is 1, so this is 2 minus 3x minus 1 plus 2 factorial is 2, so 6 divided by 2 is 3x minus 1 squared. Negative 8 divided by 3 factorial is 8, so this is going to be minus, what would that be, 4/3? Because that would be negative 8 over 6. That would be 4/3 x minus 1 cubed. We want to figure out what's the approximation obtained. What's the approximation for the value of f of 2 obtained by using this third degree Taylor polynomial? That's easy to do. We simply will say p sub 3 at 2 is 2 minus 3. 2 minus 1 is 1 plus 3 times 2 minus 1 is 1 squared minus 4/3. 2 minus 1 is 1 cubed. Remember, you don't have to simplify, but if we do, this actually kind of comes out nicely. It's 2 minus 3 plus 3, so it's 2 minus 4/3. Right. One last thing to show you all, just as we continue to get better at working with our Taylor series and Taylor polynomials. Hopefully this has been useful and informative. Look at 2 examples real quick. Let's say that the third degree Taylor polynomial for the function f about x equals 2 is this. We already know the Taylor polynomial. This is like p sub 3 of x. We want to know what is the value of f triple prime of 2. Okay, here's a couple thoughts. We got to remember our formula, as we've always said. The kth derivative, that's a funky looking k. That's still a funky looking k. All right. The kth derivative of f at a. Oh man. Of f at a over k factorial x minus a to the k, right? we know what's the value of f triple prime. So if we're looking for f triple prime will, we know it'll live, the third derivative will live wherever x minus a to the third power, right? So it'll live with x minus 2 to the third power, because third derivative, the k is 3, so it's going to need, I'm going to look for where this power here is 3. So power is 3 right over here. So if I basically ignore the x minus a to the k part, I get this. I basically get that the third derivative then, f triple prime of 2 divided by, again, that's triple prime, k is 3, divided by 3 factorial. So that's this part. I'm ignoring my x minus 2 to the third. I'm going to look at everything else. That'll leave us 1 over 243. It's going to be equal to 1 over 243, right? Because I'm saying, hey, my third derivative is living wherever this third power is going to be. But I'm going to ignore that third power because that's that part. I want this part up here. But I know that the number, the coefficient here, is that derivative I want divided by k factorial. The derivative I want divided by k factorial is what I'm going to see here. It's going to be 1 over 243. That means my third derivative then of 2 is multiply 3 factorial to the other side. 3 factorial over 243, which that is 6 over 243, and I can simplify that if I want to. All right, there is my third derivative. Knowing that the third derivative lives in this term, I get rid of this part here. That is my x minus a term. And the rest of it is the derivative I want divided by k factorial. So 1 over 243 is the derivative I want divided by k factorial, and there we go. 6 over 243. If we do our simplification there, (243) is divisible by 3. In fact, I'll take it is divisible by 6. So we can say then 6 goes into 6 once, 6 goes into 200. Oh wait, I had the wrong thing. I'm sorry. 243 is not divisible by 6. My bad. It is divisible by 3 though. So I'm going to back that up. 3 goes into 6 twice. 3 goes into 243 81 times. That was my bad. All right, let's look at one more example down here. Let's say we have this polynomial here. It's a 4th degree Taylor polynomial for the function f at x equals 3. That's what it looks like there. What is the value of f triple prime of 3? Hey, we can go through a similar kind of thing. I know f triple prime of 3 is going to live wherever this third power is. All right, f triple prime of 3 is going to live wherever this third power is. And I know that f triple prime of 3 divided by the derivative I'm at, so 3 factorial, is going to be equal to the thing that's left after I get rid of my x minus a term. So in this case, it is -7. Again, we want to take the negative because typically speaking, our terms we count as sort of positive naturally. So what does this mean? This means that the third derivative of 3 is going to be equal to -7 times 3 factorial, which is -7 times 6, which is -42. There is f triple prime of 3 by looking at the coefficient, ignoring this part. That's my x minus a term, setting it equal to the rest of my Taylor series formula. All right, I want you to try the next 2 practice problems, and then we'll wrap up there. All right. So the third degree Taylor polynomial for the function is given here. It's third degree. What is the value of g double prime of 5? Using our formula we've been working with all day, the kth derivative of a over k factorial times x minus a to the k. In this case, it looks like a is 5. I want the second derivative, so I'm going to look at where the power is 2. This means that the second derivative of f at 5 divided by, we're on the second term, so So 2 factorial. That's my coefficient part of this, so I'm ignoring my parentheses here. That is going to give us 3/8. So what does this mean for us? The second derivative of 5 is going to be 3/8 times 2 factorial. 2 factorial is just 2, so this is going to be 3/4. All right. I'll keep on going. Oh, we don't have to scroll down. All right. Let's take a look at this one. We have another polynomial. This one's a 6th degree Taylor polynomial for the function x equals 0. What is the value of the 4th derivative? So don't be thrown off. Sometimes we end up with Taylor series whose terms are destroyed. If you go back and look at the Maclaurin series I gave you, the ones I told you need to memorize, please do memorize them. From 10.7, you'll know some of them don't have every term per se in terms of degree, right? In this case, we have 2 squared, 4th, 6th. And we have then a 6th degree Taylor polynomial. We want something about the 4th derivative of f. Okay, 4th derivative of f, I would look here. Again, I'm looking for my formula up here. A appears to be 0 in this case. So I don't have x minus something because a is just 0. So what am I going to look at here? I want the 4th derivative. So my 4th derivative of f at 0 over 4 factorial is going to be equal to, I'm ignoring my x power part, is just equal to 3 in this case. So my 4th derivative at 0 is 3 times 4 factorial. 4 factorial is 4 times 3 times 2, so it's times 1, so it's 24. There we go. Which means that 3 times 24 is going to be equal to 72. All right, hopefully this helped you get a little more of a grasp of Taylor series. Tomorrow we're going to talk a little bit more about looking at more general free response questions with Taylor series. What I want you to do for homework tonight, please take a look at the problems below on the homework page, which does include parts of some free response question and then some other good practice with Taylor and Maclaurin series. And then, yeah, some concepts to do as well. All right, take care, everybody. I'll talk to you later, and be sure you send me any questions or things and read all my announcements. Thanks. Bye.